exhaustive search, we look at another interesting problem using exhaustive search. Usually exhaustive search is not good. It is not good, not efficient. Yeah. Yeah. Usually exhaustive search related to the brute force method. Not good. Yeah. But we use that as the starting point of many solutions for many problems. Okay? Yeah. So, and we use this to help us understand why some of the solutions not efficient, why some other solutions much more efficient. Yeah. So, let's look at our problem number 12. Traveling salesman problem, TSP problem. This is a famous problem. So I think many of you heard of that. Traveling salesman problem. Okay? Yeah. All right. So the problem, given n cities with known locations. We know that there are locations, n cities. Okay? Find a tour through all these cities. You have many different ways to go through all the n cities that visits each city exactly once before returning to the city where it started. Yeah. So finally, you go back to the first city, you start. Okay? So you have a tour. Okay? Now, the question, can we, so the problem is this. The problem, so solving the problem is find the tour with the minimum total distance. Minimum total distance. Optimization problem. Okay? You have so many different ways. But which one has the shortest total distance? Okay? So we want to find that. That is the problem. Very hard problem. Extremely hard problem. Okay? Yeah. So our first view of this problem, can we exhaust all the tours that satisfy the requirement? All the tours. It is not an infinite number, right? It's a finite number. If it's a finite number, we can exhaust all the numbers. If we can exhaust all the tours, then we can compare, find the minimum. So theoretically, the minimum can be found. But why you say it is a hard problem? Why you say it is an extremely hard problem? Because if you use that way, exhaustive search way, too slow. Too slow. Okay? So your algorithm is useless. Too slow. Okay? No matter how powerful your computer is, it's still too slow. Okay? Yeah. So, all right. It looks not too hard to describe all the tours under the requirement. Yeah. We need to describe all the tours. Okay. So we need to choose mathematical representation. This time, mathematical representation is important. And so it is. How do you represent your tour in an efficient, simple, but good way? Yes. So the way can help you find a solution. So we need to find a good math representation first. Yeah. All right. So let's look at that. Yeah, but the first thing we need to solve one simple problem, calculate the distance between two cities. Okay? Yeah. So we need to assume we have the locations of the cities, n locations, x, y coordinates. Yeah. Suppose we are given all the locations, x, y coordinates, okay? n pairs. Yeah. Then, given two cities, can you find the distance between those straight line distance. Yeah. So here, actually, in the real world, we never have the straight line distance, right? So we need to follow, highway. So probably, airline, highway, yeah. But never straight line distance. But here on paper, so let's just do that straight line distance. Right? Distance between two cities. So do you still remember that formula? Distance formula? Analytic geometry? Right, square, right. Pythagorean theorem, right? Difference of x coordinate square, difference of y coordinate square, take square root, Pythagorean theorem. That's the D, distance between city I and city J. All right, so you have that formula. Okay? Very simple. Yeah. We use this formula, we can calculate the total distance of a tour. Right? So, yeah, so we have that number. Right? All right. Given a tour, we can find its total distance. Right? Easily. Okay? All right. Now, describe each tour in a simple way. Now we need to describe the tour. Right? How do we describe it? Okay? Yeah. Describe a city. How do we describe a city? How do we describe a city? Do you need to use zip code to describe it? Do you need to use the name of the city to describe it? So, what do you use to describe it?
Index.
Good. Just a number, right? Index, that means a number. Okay? So, this step we call abstraction. We do abstraction. The name is not important. Okay? The geological location not important. So, lot of factors not important. We only need one symbol for it. We only need a symbol, abstract symbol. Okay? 1, 2, 3. That's good enough. Okay? So that's the abstraction we need to use. Yeah, the simplest way to represent a city. Okay? Abstraction. Okay? Use I to represent city I. That's simple. Okay? I for city I. Okay? All right. Next, we want to represent a tour. Okay? All right. How to represent a tour? You have a list of cities. The order is important, right? Is the order important? Yeah, order is important. Okay? All right. So, can we use this way? Something like city 1 to city 4, at the end, we're back to city 1. Okay? That's a tour, right? That's a tour. Okay? All right. So, that's simple, right? Okay? All right. Yeah. All right. So, is it good enough? Yeah. So, because the goal, the reason we want to represent a tour, we want to count the number of tours we have using these n cities. Number of tours. We want to find all the possible tours. That's our goal. Okay? That's our goal. Okay? Use permutation to represent a tour. Permutation. Okay? So here, yeah. Another topic in your discrete math. Permutation. Okay? Yeah. Hope you still remember that concept. Permutation. All right? This time we need a little more abstraction. Okay? Although we have this is a tour, no problem. Let's do a little more abstraction. Because this arrow symbol, not important, right? The only important thing, the order is important. If we get the order information, that's all we need for a tour. So we can eliminate all these arrows, right? So let's do another abstraction. Okay? group them together, using comma to separate different symbols. Okay? So this is our representation. Okay? The last one, we don't need another one. We know after n, we have a circle. Okay? Back to the first one. Okay? Yeah. So we get this n tuple, right? N tuple. Okay. So another abstraction, we can use this to represent a tool. Okay? Yeah. And that's the permutation, right? Yeah. Our permutation, definition of the permutation is like that. See? Yeah. So here you can see one tool corresponds to one permutation. Okay? Yeah. Permutation, very abstract. When you learn the permutation concept, do you know why you need this concept? Because it's abstract. Not necessarily targeting anything in the real world, right? Not necessarily targeting anything specific in the real world. But sometimes you get something very concrete, something like the city tour. Now you find, oh, I can use the permutation to model this specific object in the real world. See? Abstract. Yeah. So when you learn something, yeah, many times people ask, why I learned this? Right? Yeah, so when I taught 2250, so when I taught that Tower of Hanoi problem, so one student wrote on test paper, asked me, why it is important? So what's the point to learn this in the real world? Real world, we never need to solve Tower of Hanoi problem, right? So that's not an issue. Okay? The thing is, you need thinking. In the real world, you do not solve exactly the same problem, but you need concept. You need thinking. You need that model. You need that background, right? So that's the point. All right, so let me stop here. Yeah. Oh, one student came late. So what's your name? Can you tell me?
Ben Moore.
Ben. Okay, I know that.